The broadcast is now starting. All attendees are in listen-only mode.
Good morning, everyone. Just going to wait a minute or two for everybody else to join in. But if somebody could let me know if you can hear me loud and clear and also see my screen. Thank you. Okay, I think we should begin. So thank you very much again for coming to our third webinar on SimSolid between old and new school of thought. So this webinar basically will be going and comparing the workflows. I'm going to use Inventor Nastran as an example because I think primarily most of our attendees are using this technology. It's very similar to Inventor, and then I'm going to go through the SimSolid software to just show you the comparisons. I am using single part analyses for this webinar and the previous two, just so that I can spend some time going through the nitty-gritty stuff. And then the next three webinars will be large assemblies, so you can actually see how SimSolid also compares with large assemblies. Okay, I'm just going to skip through this because I think most of you know who I am. Okay, so there is a lot of collateral available from SimSolid around how SimSolid works compared to traditional FEA, but I've just picked some areas which I want to point out regarding the most important areas, I think. So I'll compare some of them items with SimSolid. Then I'm going to go through the Inventor Nastran workflow, and it's very similar to Inventor FEA. And then we'll go through SimSolid, spend a little bit more time around how it goes through the adaptive convergence process, where every single analysis you do in SimSolid will have a converged result. And then we'll finish off with SimSolid access and support and any Q&As you may have. Okay, so I've got geometry simplification here. This is an area where most of us spend a great amount of time in the hope that we don't have any mesh errors and we don't tend to have very large meshes, so we can get quick analyses. We don't have to wait around too much. So the typical things we do are geometry simplification is things like removing some more features. Typical things we fillet chamfers holes which are not in the area of interest. And the other area is where we have, let's say, thin structures, maybe sheet metal. We then convert solid to surfaces. I know Nastran gives us that ability to convert solids to shells using something called offset mid-surface extractions, or in some cases we can do beams and bars. So there are tools available in Nastran, for example, but they're not ideal if you want the surface to be connected. And then obviously we need to do some geometry cleanup. For example, if we have any overlaps, gaps resulting from any weld preps you may have. Now, these are not something that we have to worry about within SimSolid because there is no simplification required whatsoever. So depending on the complexity of what is involved, time can be taken up to an hour, several hours in regarding cleaning up the geometry. The other big issue, well, not an issue, a headache for us, is meshing. So we need to be able to do clean up the geometry to see if there's any kinks in there, for example, because obviously it will have an impact on the meshing. On the other hand, SimSolid doesn't have any requirements to do any cleanup because it doesn't require mesh. Then obviously, as we go through the Nastran environment, there are default settings which are checking the mesh against aspect ratios, skew angles, warp ratios, or angles. And again, that doesn't apply to SimSolid. And then the big one, results convergence. How that gets handled within Nastran is that we have to go through multiple analyses to determine whether the result, primarily the stress, is not sensitive to mesh changes. Whereas on SimSolid, every single analysis we run goes through a process, a results convergence process, which I'll explain how that works. And then for single part, it's fine going through mesh convergence, going through multiple analyses, but when the assemblies become very large, then it becomes tedious. So maybe it gets, ignored, just because it just takes too long, and it's then based down to intuition and the experience of the user. And again, in SimSolid, even when we're doing assemblies, you'll realize when we do it next week, it just goes through an automatic convergence process. Okay, so what we'll do now is I'm going to go through Nastran just to go through a very simple example to determine what we would not need to go through to be able to get a results convergence. And then we'll compare the same example within SimSolid. Okay. You may recognize this example. I use this within our Nastran training course. And we normally spend almost half a morning going through the different tools and workflows available, but I'm going to spend the next 5 to 8 minutes showing you what is involved. So let's use Nastran. The workflow is very similar within Inventor stress analysis. Okay, so the first thing here is we've got the materials already assigned. I'm just going to double check that I'm using the same materials within SimSolid. Okay, and then we're going to restrain this. We have a pin constraint in here. And then we're going to put a pin constraint on this side. And finally, we'll apply a load on this surface here in the -x direction, let's say. So we'll use the same load in SimSolid. Okay, now before I begin, unless you may have come across it, there is a button here which has been available for a while within Nastran, and it is meant to be convergence, but I've never managed to get it to work. But you can try it. It does say it is global refinement and local refinement, but I've not had a great amount of success with it, especially when the geometry does not have any continuous, it's discontinuous, for example. So you can try that, but I've not had a great amount of success. Hence, I promote going through the manual process, which I'm going to illustrate now. So first of all, we're going to go to mesh settings, and we'll just start off with the default mesh. And I think I'm just going to change some settings here. This is the volume growth rate of the mesh, and we'll project these. Okay, so we've got a starting point. And let's run this. And typically we'll have an idea where we expect the high stresses. Now, just before I press OK, you can see on the left-hand side we have some warnings. These warnings are related to the skew angles, warp ratios, and that type of thing, which can be reduced to 0 if we either relax the settings or we either have a more refined mesh. So we'll ignore that for a moment. So we've got a result of 84. So typically what happens is I'm going to just duplicate that analysis. And we're just going to change the mesh to normally half the original size. And with the load and constraints, everything being the same, so we can see we can have a more uniform mesh. So we'll run that one. Now, halving the mesh doesn't necessarily mean the mesh is going to be doubled. I think in this case it's gone 6 times as much. Okay, now the mesh has slightly gone down, which is normal. So we had 84 before, 82.91 now. So let's just do a third analysis so we can compare the results. So I'm going to duplicate again. And now this time I'm not going to do a global mesh refinement because it'll create too many elements. We're just going to refine the mesh around the area of interest, which is normal. So we're just going to go and do a mesh control and pick the face option around here. And let's just say we'll half that one again. Let's generate the mesh. So this process is typical of many applications. Okay, and then we'll just run this again. This doesn't necessarily apply to if you're only interested in displacement results, but most of the times we're interested in stress results. So, and the value we were looking for is within 10%, ideally within 5% is. So let's see what we got now. So we got 87, which I think is slightly higher than 5%. So just to finish off, I'm just going to compare one more. And we'll change the mesh control to half again. Okay, so we can see the mesh is pretty refined. And I'm hoping we're going to get a result close to 87. And obviously if you have an assembly, then you may have to run these assemblies, can take longer to run. And obviously you could start from a fine mesh, and then maybe perhaps you put a fine mesh like this. Maybe you don't have to go through 4, but ideally 3 is minimum. But based on experience and intuition, you might end up just doing 2, if not 3 analyses with different meshes. Okay. Okay, that's a good sign. So that's almost very little change, almost 0%. So we can say that the result has converged, and we can take the value of 87.3 megapascals and use that for our safety factor. So what we'll do is we'll repeat this into SimSolid. But before we do that, I just want to go through a couple of things. So what have we got here? So we have these results, different results. So we can see the differences are very small. And the final result, we have a 0.6% difference, almost 0. So let's see what we get in SimSolid. Now, as I said, there's a lot of information in SimSolid if you get to download the Altair ebook, but the one I'm interested in is this part here. It goes through various error analysis and repeats the process until the results are minimal or the error analysis percentage is very little. It goes to displacement error analysis, it goes to force error analysis, and it goes through displacement and energy convergence analysis. So it doesn't just go through one process, it goes through many, and then it goes through the process. And we can set this within SimSolid. Typically, if you want to converge the results for these displacements, it goes through 3 passes. And if you're interested in stresses, then there's a default setting and it goes through 5 passes, but you can use the custom settings and change that, which I'll show you in a moment. So let's fire into SimSolid. Okay, so here within SimSolid we have the same part with the same material. And so the first thing we'll do here is let's assign the material, because we brought the material, well, it didn't come through a step. So are we going to use steel using the same Young's modulus and portions ratio? Okay, and then we can go into static linear analysis, and we'll do the same thing we did before. We have a pin constraint here and another pin constraint, and then the same load. In the X direction. Okay, so what happens here is before I run the analysis, we can do a rigid body detection. Now, even though you've seen this before, but let me right. Within SimSolid, if I click on here, this is the default option. So this runs very quickly so that we can get the feel for the boundary conditions are in the correct orientation. And it goes through convergence based on displacement results. And then the second one is adapt for stress. And that goes through 5 passes and it converges against the stress results. Or you can override all this and you can basically pick and choose how many passes you want to go through, 3, 4, 5, and 6. It goes up to 9, 10. And then you can also include small features, and if it's thin solid, especially for fabrications and welded structures, you can include that as well. Obviously this will take longer. So what I'll do is we'll go through 3 different options just to give you an idea what type of results we're going to get. So I'll go back into adapt for stiffness. And let's run that. Okay, as you can see that was very, very quick. So that's just not one analysis, it goes to 3 different results. So let's get an idea for what the stress is. Okay, so the stress is a little bit higher than what we had got in our Nastran. It's around 100 megapascals. So what we're going to do here is we're simply going to duplicate this. And what I'm going to do here is I'm going to change these settings and I'm going to just use custom for a moment. So the difference between this custom and the one we did previously is that we're going to include small features, this radius here, and it will still run through the same amount of passes as it ran through the adapt for stiffness. So you can see down here at the bottom of the screen, it's going through different iterations and passes. And you can see it's taking a little bit longer as expected. Okay, almost. So let's have a look at the result. And the maximum result is 89. So, okay, so slightly Well, it's gone down slightly higher than our Nastran. So what I want to do here is just one more. We'll clone this again. And we're going to use a default. If I change the pass one more time, I mean, I could use this adapt for stiffness, which goes through 5 passes, but I'll use this one here, the customs, using adapt to features, so just one extra pass. But there is no harm in actually going straight to the adapt for stress. I just want to go through the different sort of results you might get. I mean, the changes will be very, very small. Okay, so let's go into the final pass. Now, one thing to note here is if you want to compare the results in something like Nastran or Inventor, it's not so easy to flick between the results. The only thing you can do is make a note of the results or make a copy of the images and compare them. Here I'm simply going to show you how easy it is to compare the results by creating thumbnails and comparing them. Now you can see this one took a bit longer than the previous one, and then the adapt for stress will probably take a little bit longer. So I'm just going to stop here for a moment. And we have a result. This is dropping down again to 88.7, and it might drop again if I do the adapt for stress. But what I'm going to do here is just zoom in here, and I'm going to let's compare them. 88. And then what you can do here is, so that's the final result. If I go back to the second one, you can see how easy it is to compare the results between the 3 different analyses. I'm just going to skip the adapt for us. Tell you what, let's just try it. We have time. I mean, you could have gone straight to adapt for the stress, but let's see if the results get slightly improved or not. So this will go through one extra. It'll go to 5 passes. So it'll take a little bit longer. I mean, so the result we had got in Nastran was 87.3 and 88.7 within SimSolid. And let's see if the result actually gets a little bit more refiner. But the good thing here is that we don't have to keep duplicating the analyses and run it 3 times or 4 times. It goes through one analysis. So if you were to go through this, if you're interested in stress results convergence, then you probably would go straight to adapt for stress. But I just wanted to show you the comparisons between the different passes. So this is going to the pass 4. Okay. While I'm waiting, if you have any questions, probably take another minute or so. Okay, that's done. So let's check. Okay, so you can see here we didn't get any improvements from the structural 3, which was 4 passes. So we'll stick with this one and we can assume the results has converged. So let's go back to our PowerPoint where I've actually got the results compared. So 87.65 and 88.7, you can see here we have a very, very small difference between the results of around 1%. So we can clearly see that the results are accurate. We can compare the results with similar to other traditional FEA softwares, but we can get the results a lot quicker. So I get this asked many times, but that's the link to download the trials. If you go to our Symmetry site, you can't find it, and I'll explain that because the reason why you can't find it. So if you go to the products page, so if I just go to my products page, just one page back, you come to here, and most of it by default is on the Symmetry Autodesk products. Now, if you want to find SimSolid, you can see it doesn't appear. So you've got to pick on third-party products, scroll down, click on simulation, then click here. This is where you download the form, and then that will take you straight to the Altair website. Okay, so just remember that to click on the third-party products and in the area of SimSolid. Okay, and just very briefly, if you want to take it for a spin, there's full support available. I've known some of you have actually also volunteered or attend one of these courses delivered by Altair, and also some have been in touch with ourselves with some benchmarks, but obviously we are around during these uncertain times to give you some help on something new, doing self-development. So I would recommend to download the software, and you'll be amazed how easy it makes simulation. Okay, and from next week onwards, we will be starting to focus on large-scale models, and we're starting off with welded fabrications, and the one after that will be bolted connections, and then very, very large structures, which make job analysis with the Nastran a lot more difficult. Now I'll hang around for a minute or two for any questions you may have. Okay, if you have any questions, you by all means send me an email. And again, thank you very much for attending the webinar this morning, and I hope to see you guys to our next webinar next week. Thank you. Have a great day, guys.